very nice to see you here, and let's start the session. My name is Andrej, and I'll talk about MLOps with FastAPI, RabbitMQ, and Kubernetes. Okay, so agenda, what you should expect from this session. First, I'll introduce myself in a few more details so that you would have a bit more context. Then I'll talk about Skipper. This is our open source tool that we are developing, and I'll explain why we are developing and why it may be useful for you. And I'll talk in general about MLOps microservices. Then we'll see live demo. And if there'll be still time left, I'll go through the code and to try to explain the main concepts. And also I'll talk about infrastructure. Okay, so few things about me, because yeah, I'm kind of, it's my first time talking on Python conference in Lithuania. So first of all, I'm from Lithuania, from Vilnius. Back in 2007, I finished Vilnius University Math and Informatics faculty. Since then, actually, I joined a local company which was called, maybe not very creative, but it was literally called Information Technology. That was the name of the company. It doesn't exist anymore. It was acquired by a few other companies, but it was a great company. And their focus was on Oracle. And this is how my IT career started. We focused on Oracle, and then from like 2005 till 2018, I was focused on Oracle, and then I started my own company, Red Samurai, with Oracle Consulting, and was traveling a lot in different places, and mostly working abroad. Not Lithuania, but I was still based here. But then in 2018, I thought, okay, maybe I need to change, and I decided to completely change the way I work. I still manage Oracle business, but myself, I don't do any Oracle work anymore, and I switched completely to open source and Python. And the main reason for that was because Python is a very popular language, but obviously it's not the main reason, but the main reason is that there are lots of open source libraries available to implement ML solutions with Python, and we decided to build our own product. Yeah, so this is what we're doing now. And I'm trying to, because there are lots of open source code, tutorials, videos about Python, and this is how I'm learning about Python, but at the end, I'm also trying to give back to the community, and I have my YouTube channel, and whatever I learn during week or whatever I implement during week, I try to publish online as a video or as a blog or some sample code, because based on my experience working with Java and Oracle, it works great when you contribute back to the community, and this allows you also to learn something new when you actually contribute back, because when you build a sample or create some tutorial, at the same time, you're not only teaching or sharing knowledge, but also you're learning yourself as well. Okay, so this is just a few words about me. And the main topic of this session, Skipper. So, yeah, we decided to build our own ML product. And then we started to think like how, okay, we'll build this product, but how we would run it in development and in production. And we did the research, spent quite a lot of time, and we saw that there are existing solutions like a Kubeflow, Airflow, that these solutions allow to run containers either on premise or on cloud, and you could orchestrate your ML workflow or ML pipeline, and they work great. But then still, I was thinking, okay, those solutions, they're kind of heavy. And if you want to build something lighter, more flexible, more configurable, you would need to spend a lot of time in researching like a Kubeflow or any other solution. And Kubeflow is very heavy in terms of resources also. So if you want to test it on premise, not on cloud, then you would need a very powerful machine, lots of gigabytes of RAM and so on. So I thought let's take those open source libraries that are available and let's combine them together and build some sort of a template. I would not call it like a product. It's more like a template with a predefined set of scripts and instructions that anyone could take, and anyone could modify containers that are included and add their own containers, remove containers, and quickly spin up on-premise or on cloud. And it should run either with Python virtual environment, with different set of virtual environments, or should run with plain Docker with different containers, or if you need more scalability, it also can run on Kubernetes, either on local one or on any cloud vendor. And it's completely open source on GitHub, and this is for us, this is infrastructure that we are using to build our products that some use cases. This is like a foundation, and anyone can use it as well. And to give you high-level architecture overview about what I'm talking about, so Skipper and this MLOps thing is focused on microservices. And why microservices? If we talk about machine learning domain, very often you would see developers, they go and they create Jupyter or Colab notebook. They do research, they build model, they transform data. The model is great, model is trained very well, and then they run predict functionality, everything is working fine. And they end up having like one big chunk of code which works fine, but then as time comes to deploy it or integrate with the main system, they face a challenge that it's kind of not flexible. And even worse, it comes later when you need to do maintenance, and if data structure is changing and you need to go and update the logic to make sure that data parsing is updated and so on, then it's, the risk comes that you may break entire pipeline and so on. And this is actually we faced ourselves when for one of the customers we were building some forecasting solution based on ML models. We had one big monolith application, and at the end, when data structure was changed and we needed to update it after half a year, it was a big challenge to find the place where change needs to be done and so on. So after that, I learned that to build proper ML solution, we need to use different containers, different services. And the word microservice doesn't mean that service should be like very small. No, it can be big. It can be like some data transformation logic, which maybe have a fair amount of code. But the main thing, you should split code based on use case. So, for example, data transformation preparation logic should be one container, then model training should be another, and model serving and inference prediction should be another one. And this would allow to maintain the code better and easier. So, yeah, then we started to look into infrastructure, as I said, and we created 3 different services: data training and serving. But then we need to communicate somehow between those services. For example, when request would come to train the model, then this container which trains the model, it somehow needs to ask a container which creates data, please give me the data and send me the data. I'll use this data to train the model. So this means there should be some communication between services. So there are multiple patterns in microservices how you implement communication between services. And I think what, at least in our case, the optimal one was to use RabbitMQ. There is also Kafka, but I kind of I preferred RabbitMQ because of very simple and clear Python interface. And on top of existing RabbitMQ Python interface, we created our own wrapper, skipper-lib, which makes calls to RabbitMQ very generic. And if in future someone who would be using Skipper would like to use Kafka, for example, they could replace RabbitMQ with Kafka, and everywhere in all the containers where API calls are made for communication layer, the code would stay the same because skipper-lib hides the specifics of RabbitMQ Python API. Okay, so communication is done through RabbitMQ between all the containers, and we have on the left side you see generic engine, and this block is also based on multiple containers. All the yellow boxes are separate actual Docker containers, as you see here. So this central part is FastAPI, and by the way, the creator of FastAPI here is in the room. So thanks for that. And FastAPI allows to easily implement REST endpoints, and it's a very light tool. Doesn't need lots of resources, and it's very flexible. It comes with a very nice UI which displays the REST API structure. Also, you can do groupings if you have REST API. You expose REST API, and you know that there'll be certain groups, so you can create groups to improve readability of your API. And there's Nginx in front as HTTP proxy to serve API to the outside. Then there's a Celery container which helps to implement asynchronous, to process asynchronous requests. This means when a request comes to FastAPI, and if you know that this request is like for training, for model training, which is long one, then we execute this request through Celery. We put it into the Celery queue, and it means that Celery would take care for the request execution in a asynchronous way. When request will be completed, then Celery internal storage will be updated, and it will have the information that this task with this specific ID is completed. And at any point of time, we can check the status of the task and see if it's completed or not. Then there is a workflow and logger. Those two are custom components, and if someone is using Skipper, he's free. He can either use this workflow and logger, or they can replace with their own components. The idea of workflow that it should have a logic which would be able to understand if this specific task should be executed asynchronously or not, for example. And logger provides the endpoint where you could submit any action from any of the containers and basically log them into the central place. Yeah, and all of this runs as Docker containers or on Kubernetes. Yeah, so this, just to summarize, so the engine containers Nginx act as HTTP proxy. Then there's a FastAPI as a REST API controller. Workflow implements navigation. Then there's a Celery for asynchronous calls processing and logging to log all the events. And all the stuff is implemented with Python. Then we have communication container, which we're using a standard image of RabbitMQ in a separate container. And there's a wrapper skipper-lib, which is a reusable library published on Python library index. And also there's another version of implemented with JavaScript is published on NPM. And it allows to use different languages in this infrastructure, like Python or JavaScript. So, for example, your model training code can be implemented with JavaScript on Node.js, for example, and you can still plug in this container into this infrastructure that implemented with Python. And there's a sample set of microservices for data training and serving, and those are created just as example to show you how the infrastructure works. And obviously, in your use case, you would need to replace that with your own components. But you can follow the example and see how API calls are implemented, how the scripts are set up, and you could add your own containers or use the existing ones. So it's up to you. Okay, and all the code is on a GitHub, and it's implemented as it's set up as public template. And the idea is that you could either clone it if you want, or you could create your own repository, and you can map your repository with the template. And then in future, when you will see that there are some changes we implement in this main template, you can, if you want, you can sync them into your own repository, and this way you could stay up to date. Because if you would clone it, then you're on its own, and you would not get updates that we would implement in the future. So, but it's completely up to you. So in terms of infrastructure, as I already mentioned, that just to repeat it, to be more clear, that there are multiple runtime options. First one, you could run all those containers as a separate processes on your own computer with virtual environments. Another option, you could use Docker containers or Kubernetes. But there are some specific cases where if your model, for example, you want to train it on GPU, then it's not so simple to do it through the Docker container, because when you run code inside Docker container, it's tricky to leverage and utilize GPU on your main machine. So you may, like model training, you may run, for example, not on Docker container directly on your own machine, but communication with other containers still would work, because RabbitMQ runs as independent container. And for RabbitMQ, there is no difference from where the request comes, either from another container or from the code that runs locally on the machine. Yeah, and as I said, that this skipper library, wrapper library for RabbitMQ API is published on Python library index and on NPM, and you can install it directly from there. Also, all this template and all the scripts are tested with different cloud vendors, and like with Google Cloud Engine and with Oracle. I didn't test it yet with Amazon, but the reason for that is because I prefer to run Kubernetes on Google. For me, it's somehow easier and more flexible to run it on Google. Okay, then let's see how it works. And most of the session will be not with slides, but I actually will show the stuff. So. Yeah, just to give you a heads up what I'll be showing, like Kubernetes infrastructure setup probably a bit, and also I'll show how asynchronous REST API call is executed and handled by FastAPI and Celery. Then obviously RabbitMQ runs and it orchestrates all the events across pods and containers, so this is included as well. We'll see RabbitMQ dashboard, and we'll try to execute multiple requests very quickly to make sure that asynchronous requests are executing in parallel. And interesting part will be Kubernetes pod scaling. I'll scale one of the pods to multiple instances, and we'll execute few requests, and we'll see that first request handled by one pod, second request is handled by another pod. So we have some sort of clustering. And yeah, if there'll be still time left, I'll show you the source code, and I'll explain main things about the source code. Okay, we'll switch to the desktop, and I should record the screen, because later this session will be available online, and the screen recording will be included. So let's. Okay, recording is on. So first of all, I'll run everything through command line. I think the font is visible. I was trying to increase it, so it should be visible from the back as well. And the first thing, this demo I'm running on local environment, and I run it on Docker on Docker desktop. So it's both engines are up and running, Docker and Kubernetes. There are multiple ways how you could run Kubernetes locally, but I prefer Docker desktop because it simplifies usage of the Docker images, because there are other engines, but then you would need to publish your Docker images on some external, for example, Docker registry, and consume from there. But if you're using Docker desktop, then Kubernetes that runs inside Docker desktop, it out of the box understands, and it can see Docker images that you created inside Docker, obviously. Okay, so first of all, to able to access RabbitMQ dashboard, I open proxy connection to the RabbitMQ, and then I could go over here and test. Yeah, the page is accessible, and that's because infrastructure runs in Kubernetes, and by default you don't have external communication to Kubernetes pod from the outside. So you need, for the development purpose, you need to explicitly open the port for RabbitMQ inside Kubernetes pod for this port to be accessible from the outside. Okay, then we can check that we can double check that infrastructure is running, and what we have here is, yeah. By the way, maybe first I should go to the GitHub and just briefly show you the structure of the skipper. So all the environments, all the infrastructure that I'm showing to you, it's very easy to start because all the scripts are available, and whatever I'm showing to you is you can spin up. For example, if you go here, you can see that there are instructions for Docker Compose or for Kubernetes. So this is what I'm using here now. And in case of Kubernetes, you install Nginx and ingress controller. Then you build images with Docker, and then you run Kubernetes setup script, which creates everything, all the pods, all the infrastructure. And then API becomes FastAPI application is accessible on this internal URL. And yeah, so this is the main point of Skipper is that it's light, simple, and you don't have to do any complex things to spin up your containers. You just run script and so on. And if you want to change, it's easy. You go to the script and change it. Okay, so in terms of infrastructure, we have now different Kubernetes pods, and Kubernetes pod is the simplest, the smallest object in Kubernetes that you can have. And Kubernetes pod can run either one or multiple containers, and those containers are created from Docker images. So as we see here, most of the pods, they run single container, like this is FastAPI pod, this is Celery pod, this is Logger pod, then there's a workflow, training service, it's a single pod with two containers. And Kubernetes have a very nice concept of a sidecar container. And sidecar container concept means that in a single pod you can run main container and helper container. And it's very convenient because when two containers run in the same pod, they share the same infrastructure, the same network, the same storage. So in this case, helper container, what it does, it's managing the model which is trained. So when main container trains the model, builds the model file, the helper container takes this model file, it makes the serialized copy of this model file, and it's posting this model to the RabbitMQ, so that all the subscribers that need to get this model file, they'll get it. And this works when model file is small, when probably you work on tabular data. But if you work with complex models, or you're fine-tuning some models like from Hugging Face, they're usually huge. So then it would not work to post the model through RabbitMQ and distribute it through RabbitMQ message to other containers. Then you would need to use some external storage, either on-premise or on cloud, and you would post the model to external storage, so that all other containers would consume this model file not through internal RabbitMQ messaging system, but from the external file storage. Okay, and we have spinned up here two pods for the serving service, because usually in real life the model training would execute. You would not run multiple model trainings at the same time, probably. But when model is created, you need to serve this model to the public, to the users, to your API, to the application, and at the same time, model could be used by multiple people, by multiple sessions, and you need some scalability here. So for that reason, in default example of Skipper, I included 2 instances of serving pod just to show how request is being executed by first pod and by second pod, and this way the clustering works. Okay, so now let's open logs. So late in the next step, when I execute API call, you would see information printed on a log, and it would make sense how the request is being invoked. So this one is log for FastAPI application. Then over here we have a log for salary container, which, as I said earlier, allows to implement asynchronous requests. Okay, then this is the port for the model training. And over here we have first port for the serving service, and just I should double check that the instance name is correct. It ends with XWXDV, so yeah, this one is correct. Okay, it's up and running, and it's for the second one is TR. Yeah, that's correct one. It's over here. And the last log window would be okay. I think I closed by mistake. So let's open. Let's copy them. Let's make it wider. Okay, this one was closed. Okay, this one. Training. This one is serving first. Okay, this is the serving second. Fine. No, actually, this one we don't need, and this one is for mobile net. Okay, so all the logs are open. It seems like now we can go and see if FastAPI in general, FastAPI endpoint is responding. So we go to this default UI page that's out of the box generated by FastAPI tool. We refresh it, and this like very basic endpoint to test if infrastructure is running in general. So you get it out of the box from Skipper. So we click execute, and we see that API is running. That's fine, and we go to this log window, and if I clean it up and execute a few more times, we see that the log is printed. So the pod which is responsible to run FastAPI application is responding fine. Okay, so the next thing would be we need to train the model. If you want to allow users to run inference, then we should have a model, and we train the model. In this in default Skipper example, I'm using Boston housing data. It's a small data set, just for example purposes. It's not supposed to be some complex ML model which trains for a long time. It trains just in a few iterations very quickly, and the main point is to show that the model trains, and it's not there is no point to show some sophisticated model. And by the way, model training is done with TensorFlow and Keras, but in the same way you could install PyTorch and build models with PyTorch if you want. Doesn't matter. So we go over here and to say that we use 80% of data for model training and 20% for validation. And we execute the request. We get back task ID. And if you go to the salary log, we see that task is already completed. This is on purpose. I'm not running very long model training just because I want to save time mainly for during presentation. But this request is asynchronous because the idea of model training that probably it would run long. And this is the reason why when we execute the request, we get back task ID in response. We don't get information that model is trained, for example, because model is supposed to train maybe for half an hour, for 1 hour, and so on. So I can take this ID and I could scroll. There's another standard endpoint from Skipper that allows to check the status of task based on the ID of the task. Okay, I'd copy paste the ID, execute, and we get the status task completed. If the task would be still running, then it would be a task in progress. Okay, and now I could go and simulate a couple of requests in parallel. So for that, let me go and clean up the log for the salary window. And by the way, before we would run, if I switch to another log where training pod is running, we see that log was printed out for model training, and this means that training was actually executed in this pod, and there was no errors. So now I cleaned up log for the salary window, and I go and click on execute multiple times quickly, like 1, 2, 3, 4. And then we go to the salary, and all those tasks are executed in the backend asynchronously. Response was returned quickly to the FastAPI from salary without blocking the original response. And this is in particular important for web applications, because when user runs a long task, user don't want to wait until this request maybe for 10 minutes, maybe for half an hour would execute, and user don't want to see like a UI blocked or whatever. So for that reason, you want to implement asynchronous request and return response instantly, and you want to let salary to handle the request in the backend, and later when request will be completed, you may have some UI logic or backend logic which checks, which polls, for example, or maybe some through the WebSocket you may check task status ID and inform the user that task was completed, and then user can come and see the results. So now we can see that I clicked like 4 times to execute, and we get back 4 statuses are returned in the back to show that all those 4 tasks were completed successfully. Okay, so we trained the model, and if we check the RabbitMQ, we see that on the queue section, then we have like a queue name for Skipper training, serving, MobileNet, data, and so on. This means that when request comes to FastAPI, and then it's routed to, if it's a synchronous one, it's routed to salary, and from salary we call RabbitMQ. We send the message that, hey, we want to execute model training. And then RabbitMQ goes and checks who are the subscribers for this message, if there are any subscribers for this queue. And it finds that this pod, model training pod, actually subscribes to the queue, and RabbitMQ delivers message to that pod. And in case, what is great about RabbitMQ is it supports clustering out of the box, message distribution to multiple subscribers. So if you would decide to spin up training pod and create two instances, 3 instances or more, then when each instance is created, RabbitMQ would automatically get information that there's a new subscriber. And by default, when there are multiple subscribers to the same message, when the message arrives, RabbitMQ would distribute it to the first subscriber. Then when the second message comes, it would go to the second one and to the third one and so on. So it makes a round robin out of the box. And this allows to distribute your load on the application evenly. And there are some use cases when you want to fan out the message to all the subscribers at once. So when message comes, you need all the subscribers at the same time to get the message. And then you just need to change the property of RabbitMQ for this specific queue, and say that you want to use fan out mode, and then it will be distributed to all the subscribers at the same time. And this RabbitMQ functionality plays very well with Kubernetes, because on Kubernetes it's easier to spin up pod to create more instances or reduce instances. And since RabbitMQ automatically is able to track all the subscribers, you don't need to do any extra job, any extra implementation to support Kubernetes, the way how Kubernetes scales, because when new instance of Kubernetes pod will be created, automatically RabbitMQ will register a new subscriber and will allow communication with that subscriber. So it comes out of the box. Okay. So now we trained the model. So the next step would be to try and use the model. And there's a separate endpoint called predict for that. We click try it out, and before I would execute it, I would go to the log which displays output from the first pod, and there's a second window which displays output from the second pod. So let's clean it up, and if I click execute, I get back the result. Now prediction was executed. The model which was trained was used to process this payload, and this is it's a sample payload. You should again, it's created just for demonstration purpose, and the idea of the model that it should try to predict the house in Boston based on some historical data. Based on data is constructed on different parameters, like number of rooms of the house, when the house was constructed, and so on. And this is done just for demonstration purpose, and I don't have a goal to execute proper prediction here. But whatever it returns some price and some ratio over here. And then if you go back to the log, we see that in this case, this request was handled by the second pod, because the log was printed out when this model prediction was executed. It was printed in the second pod. And if you click once again, then it gets the log also printed on the first pod. This means first request was handled by the first one, by the second pod, and the second request was handled by the first pod. So this load distribution is working as expected. Okay, and there's another service. It runs with JavaScript, with Node.js, and using TensorFlow.js. And TensorFlow.js allows to implement model training and inference with JavaScript, and it runs in a separate container. And the reason why I included it into this default skipper template is to show that we could also integrate containers with JavaScript, and they could run in the same infrastructure which runs on top of Python. Okay, so let me close this one, and let's open this last endpoint, and I execute it. And if I go back to log, we see that request arrived, and what this model does, it's using standard MobileNet model. It gets image and it tries to predict what is in the image. And in this sample, there is some picture with orange, and it returns probability that 98% this is orange. Okay, but now if we look into the infrastructure, we see that there is one port for this MobileNet service. And what we could try to do now, we could scale the number of ports to 2, and we would have like 2 ports to handle MobileNet. So for that, let's go to the let's copy the instruction how to scale up the ports. We go to the folder which implements service, a sample set of services, and we go specifically to MobileNet service, and each service in Skipper have a README file, and this is created for that reason because maybe you would like to run just one service and see how it works, and you don't want to run entire infrastructure. So you could go to the actual service and see the steps over here. So what we want to do now, you want to scale MobileNet service to multiple instances, and with Kubernetes is done very easily, just one line of code. We provide the name of the pod, MobileNet service, and we say how many replicas we want to have. In this case, we want to have 2. So we execute, and it says that the pod was scaled, and we could review the infrastructure, and we see that new pod was created just now, and it's already up and running. Okay, then we could go and open one more log window, which would display the log for the second MobileNet pod. For that, we need to copy the ID of the pod, which was created just now. This is the ID. Okay, we'll go over here, delete the old ID, which was created before. Okay, it's up and running. I can clear up the log. And now if I go back to FastAPI endpoint, I click execute once, and we see that this request was handled by the first pod. There's nothing printed in the second one, and we click once again. Then log is printed in the second pod, and this request handled by the first one. If we click one more time, then this third call is handled again by the first one. So this is default round-robin messaging from RabbitMQ, because we created second pod, second subscriber. As soon as this second pod was created, it registered itself with RabbitMQ. RabbitMQ now it's informed that there are 2 subscribers, and when requests are coming, then they are evenly distributed across the pods to make sure that we split up the load. And the beauty of Kubernetes in this case, that it's simple to manage the instances of the pods. In this case, I was doing manual scaling, but Kubernetes allows to do auto-scaling. When you run in production, you can define rules that would allow to auto-scale the number of pods based on the traffic. So if you would, during the day, you get more load, then the Kubernetes infrastructure could auto-scale to multiple pods. At night, it could scale down and so on. This is especially important if you run your solution on cloud, because you don't want to use many pod instances all the time, because you need to pay for that. So you could scale down to reduce the costs of the runtime. And now, if I would go back to this log window, I would say that okay, I don't need 2 instances. I just want just one. I scaled it down. If I go now to infrastructure, I would see that the instance that was created just a few moments ago, it's terminating, and it will be automatically removed by Kubernetes engine. Okay, so this is runtime, and my point was to keep it simple, not to overcomplicate it, because I believe it's important to show like the main points, and if you would find it useful in for your daily work, then it would help to create a better idea in your mind how it works and how it could be usable for your own use cases. And maybe now we have some moments left. I could go and give brief overview in terms of code, how you would use this solution on your own. So as I said, that in the main README file you got all the instructions how you could start it with Docker Compose, with Kubernetes, and you need to, if you run local Kubernetes, you need to install a load balancer by yourself. You go through by that link, and it's Nginx documentation, and they describe multiple use cases. If you run Docker Desktop, then there's one way to install load balancer. If you run other tools, then there's another way, and so on. If you deploy it on cloud, then load balancer usually provisioned automatically. You don't need to install it separately. Then all the components are described, and yeah, there are references to libraries on skipper library on Python index and on npm. Okay, and if you look now into the API, which is the entry point, it handles REST calls from the outside, and it's the place where initial request is handled, and all the other job is executed from here. So we have, you will find YAML files which would describe infrastructure for Kubernetes, like how the pods are created and so on. Then there is a Docker file which describes how to create the image, and the same structure is repeated for all the components, like for API, for workflow, for sample services. So the same structure is everywhere. And then we got endpoint. This is the main Python script, which is automatically invoked when container is starting up. Then endpoint is initialized out of the box. Then because this container implements FastAPI endpoint, so we're using FastAPI, we define the URL, which is accessible through the host from the outside. And then we create multiple groups here. So the first API group defines Boston housing related model API, and the second group is mobile net related. And I created this example on purpose, so you would see how you would create different groupings, and if your API is large, it's convenient because then API is not listed just in a single list, but in separate groups, and it's easier to navigate. This is how it looks like. This one is default group, just a basic call to see if API is running. Then there's another group for Boston housing. Then there's another group for MobileNet. Okay, and then we go to API, and there is go to this each API group is implemented by different script, and this is where you define with annotations. You define FastAPI endpoints, like this one. This is the method handles task training. This one gets task status, and this one executes prediction. And it calls all the methods are calling helper libraries from helper API calls from the skipper library, and as I mentioned before, this allows to minimize the dependency on RabbitMQ, and if you decide in future to switch to like Kafka or other options, then it's kind of easier. Okay, and let's see. So we have multiple routers for different API groups. Then there is worker is defined for salary to implement asynchronous request processing. And then if you would go to, that's about API, if very briefly, and if you go to services, let's go to serving service. The serving service gets request when you want to execute prediction based on model which was trained, right? So there's a main entry point which is executed also when container starts, and it defines event receiver over here, and event receiver is also coming from the skipper library, and event receiver main job is to register this container with RabbitMQ. And over here we point to the serving service. This means then that when event will be received, this event will be handled by serving service class. Serving service class is implemented in the same container under app folder serving service. And there's a definition for serving service class, and we got a method, call method, which is the standard method which handles the call automatically when this container gets a message from the RabbitMQ. And over here we are parsing the payload that is transferred through RabbitMQ message. Then we open up, load the model, execute predict functionality, and send back the result. So this specific service, it handles event, and it doesn't produce any event. And this another example of in training service, we receive event and we also produce event. We produce event because we want to talk to the data service where data will be prepared for us and returned back and ready for model training. So there is the same main entry script which defines receiver. Then it points to the training service class, which also defined under this APP folder. This is the training service class implementation. There's the same style is used over here. There's a call method which is invoked when message is received. And then when message is received, we do different steps, and one of them is to prepare dataset. And over here we use event producer, and we send the message to the RabbitMQ, and we say that we want to queue for data container. And in this case, RabbitMQ will receive the message from training container, distributed to the data container. Data will be prepared there and returned back in this response. And in this case, this is not asynchronous call. This is a synchronous call, because we need to wait until a response will be produced. We don't want to move next. We need to wait. And when this request is being executed, RabbitMQ allows us to do a wait, basically, and execute it in a synchronous way. Yeah, so this is quick summary, and yeah, so we are using it internally for ourselves, and there are I know I was in touch with some people just from online. They are also using it to run their own infrastructure. So in terms of summary, during this hour, what I was trying to show and explain this simple MLOps pipeline, which you could use to run your own ML services, but it's not only ML specific. You could run any workload. The container that runs the service could run any logic. It just, in terms of skipper, we were trying to build a few more examples to show how it would run with machine learning use cases as well. It's completely configurable, customizable. Everything is open. It's easy to change up to your requirements. It runs on premise or on cloud, and it runs either with Docker and Kubernetes. So thanks, and yeah, maybe some questions. If there will be any questions now, I would be happy to answer. Okay, so thanks.